So the primary purpose of this video is to talk about the R-Shiny, however, or analyzing R-Shinies, or using R-Shinies to analyze real data. But here we have to notice, okay, so this is some real data. This is from the New York Times. It's important to note. It's a map of segregation. We're looking at Chicago. You can look at different cities, but Chicago is very interesting, right? And so with that being said, we also need to mention, or at least talk about the individuals, the authors that made this plot, and also where they got this data. So this is from 2010 census, and this is from the 2015 article, news article in July 8th. So what we'll do is we'll look. I mean, this is not class, but you can imagine, you can look at this actual plot and see some generalizations, really obvious generalizations, like in different regions of Chicago. And this is not only in Chicago. So what we're going to learn is something called a chi-square goodness of fit. Or at least I'm going to kind of talk about it. So a chi-square goodness of fit is the capacity to determine if what you observe matches what you expect. What you observe doesn't match what you expect. So let's say you have a definition of diversity, okay? This is an interesting definition of diversity, but let's say that each race is equally likely. What that means is that what we would want to see is, does a particular census block actually match that claim? Is it 20%, 20%, 20%, 20%? I think that's 5 for all of the races, okay? For Asian, Black, Hispanic, other, and white. So what we can do is we go here, let's choose this one, census block 330100, right? And we have Black observed is 26%, 6% for Hispanic, 14% for Asian, 51% for white, and 3% for others. And then we have 16,000 individuals. So I have to enter all this information. So let's do this. I'll pause it and I'm gonna enter it, okay? I'm gonna pause it and I'm gonna enter it. Okay, so I entered the numbers. The sample size, I believe it was, I didn't enter that. It is 16,735, 16735. And so some intuition, or at least some knowledge of this, we know that if the test statistic is large, the p-value is small, meaning that there's a huge difference between what we expect and what we actually observe. So let's see if our test statistic is large and the p-value is small. Okay, my test statistic is 12,701 and my p-value is 0. So the likelihood of us actually seeing this by chance is so unlikely, okay? And so what I did during the break, I actually took this makes sense because equally likely, it's not equally likely, it's based on these numbers. But what I did during the break was I went ahead and got the actual country's numbers. And mind you, there's an issue with this because this is from this data is from 2010. Cities change, but that's for us to at least be aware of, okay? This is 18.5. This is 60.3, and this is 1.9. Okay, so 1.9, and we still keep it 16,735 because that is our observed sample. So what do you all think? Do you think we're gonna have a small test statistic or a large test statistic? Okay, I would argue I think it's gonna be a large test statistic. Not as large as this, but it's still gonna be large. Let's see. 5,603, and our p-value is essentially still 0. So this actual census block does not match the demographics of the country. What's really interesting here is that I try to choose a block that seems diverse. None of these other blocks are like that. It's very segregated. Very, very segregated. Okay, that's it.